Hello, everybody. Welcome to day 11, the first day of the second unit of CS54. We've spent the last 5 weeks learning how to program, write functional programs in Galena, the functional programming language inside Coq. It's been a bit of a journey. We learned a lot about data structures. We wrote a bunch of interesting recursive functions and sort of ended with two nice case studies, one being Levenstein edit distance, a way to think about how to compare different strings, in that case DNA, and then one about how to write little interpreters and compilers for arithmetic languages. So we've come pretty far. We've written some interesting programs. And what we're going to spend really the whole rest of the course doing is thinking critically about programs and other definitions. You know, what do they mean? Do they mean what we think they mean? What are their properties? What's true of them? What can we prove of them? So the way the proof portion of this course is going to work, this latter 8 weeks or so, um, is it's going to be all in two sections. So the first section will be formal proof using the tools in Coq to prove things about programs we've written in Galena. And then after that, we'll sort of take a left turn and start doing informal proofs on paper about definitions we've written in Coq, but then also just plain mathematical definitions that we'll sort of finally be ready to confront on our own. I want to give you a little bit of background on why we're going to do it this way. The whole theory of doing this first in Coq is around the idea of having Coq help you learn the rules of the game, right? There's like an agreed upon set of reasoning principles, like the way that proof is going to work, what's a valid logical move, and that's a matter of convention. I mean, it's a matter of consistency. You wouldn't want an inconsistent set of rules, but there's also rules that we accept and rules that we don't accept. Right? There's just different ways of doing things. So to learn these rules, I think it's really important to have a guide. And so I'll be your guide. Our friendly TAs will be your guide. But also, Coq will be your guide. Coq knows the rules. Coq, as you've noticed, is very good at following its own rules. So it'll be like an always-on tutor who can tell you whether or not you've made a valid move or not. Hopefully this helps, and by helps I mean helps you internalize the rules for yourself. And then when we come to informal work, you'll have internalized the rules enough that you won't even need Coq's help. You'll just be able to do it. Okay, let's get started. If you're looking over here in this pane on the side, you'll notice that this is a very long list. So I'm going to try to make these videos really short, um, and we'll just see how we do. As we move on, I think the days will be a little shorter. My goal in this edition of CS54 is to have the proofs not be too intense, but we still have a lot of material to cover to sort of get all of the techniques we need to be able to do the proofs that we want. So the homework should not be greater in volume than what we've had so far, but I think some of the reading in the videos might end up being that way, just to set expectations properly. All right, with that introduction out of the way, let's focus on today's video, propositions. Okay. In the textbook, there's some discussion about why you might care about these things. I'm happy to talk about it more. I've already talked about proof, like why you might care about this formal approach in videos, so I'm not going to belabor it here. So, what we're going to do in this whole latter half of the course is we're going to work on proofs. So what is a proof? What is it that one proves? So a proposition is the class or set of things that one proves. A proposition is a statement, an utterance, that could be proved or not, right? It's something that may or may not hold. You'll notice I'm being very careful to not say is or is not true, right? Whether or not something is true is a matter of proof. Maybe something we can eventually show to be true, we can eventually show holds, but we don't know how to yet. That doesn't change whether or not it's true, but it changes sort of what we know about it. So I'm going to try to be careful and talk about propositions we've proved or haven't, rather than things that simply are true. This distinction that I'm making about our work is, I think, a fundamentally computer science distinction, as opposed to maybe mathematicians who would say that, well, look, there's some holy notional book in heaven of all the proofs that are true, and it's our job to find them. That to me is not really the computer scientist's approach. We're making it up as we go along. Okay, let's look at our first proposition. 3 equals 3. Right, so you've seen propositions before. Any equation you've ever written is a proposition saying that, well, I propose that this side is equal to that side. Some of the equations you've written might have been definitions, but this one is a proposition. If we ask Coq what type it is, it helpfully says, oh, it's a prop. Cock's busy, doesn't have the time to write addition, so prop. Prop is the type of propositions. So 3 equals 3 is a proposition. This is one that it turns out is true and is actually very easy to prove. By the end of today's work, you'll have proved propositions like it. 3 equals 3 is a proposition. Let's see another one. Here's another one. I'm going to start by reading it out loud. The text above here explains it in detail. I'll do it in my own words. So this proposition says, hey, for any natural numbers n and m, arbitrary ones, pick them, whatever, the quantity n plus m is equal to m plus n. That is to say, addition plus is commutative. There's a couple of different parts here. We already saw equality as part of a proposition, but here we can see that these for alls, which before we just saw for polymorphism, are also used in propositions to say, well, hey, give me n and m that are nats, then n plus m equals m plus n. Another proposition. This proposition is also provable. It's true that the plus that we defined is commutative. We're not going to get to it today. Okay, so far we've seen two notions of proposition. We've seen, hey, this expression is equal to that expression. Or we've seen for all x of some type, proposition that can now mention x. Okay, this is called a quantifier. This is a universal quantifier because it says for all of them, for any possible natural numbers n and m. I'm not saying you can just pick some particular n and m for which this is true, say 0 for both. That is true, but it turns out it's true for any n and m. That's what the universal part of the universal quantifier means. Okay, so this notation here, this is the sort of the Bacchus-Naur form of grammars. This is a way of saying, hey, I'm going to define this category prop, this set of things prop, that could potentially have this shape. Right now we've seen two shapes of proposition, equalities and quantified proposition. So you'll notice here prop is mentioned in its own definition. It's sort of a recursive or inductive thing. One other notational note, up top we saw for all n, m, colon, nat, or type, or whatever. That's the same as writing two for alls in a row. Let's look at some more propositions. Now, so far, we quantified just over two natural numbers, but you can write quantifiers over things of different type. For all bases b and all natural numbers n, the length of the list repeat bn is equal to n. What does this mean? If you give me an arbitrary DNA base, call it b, and an arbitrary natural number, call it n, if I call repeat bn, that'll give me a list with n copies of b. The length of that list will itself be equal to n. Oh, this is probably a true proposition. We ought to be able to prove it. Again, not yet today. Now, a thing that I cannot stress enough, every syntactically well-formed proposition has type prop. That doesn't mean that it's true or that you can prove it, right? We can say things that are not true, right? 2 equals 2, that's a proposition. 2 equals 5, that's also a proposition. This one seems implausible. I don't believe 2 equals 5. But both of these have type prop. Okay, this is false on the face of it, right? Like we know that on the left this is s of O, and this is 5 s's and an o, and that's just two different things. Okay, fine. But you can write other things that are unlikely. For any natural number n is equal to 2. I'm less sure about this one too. So universal quantification means the universe can pick any natural number n, and then that number will be equal to 2, is what this proposition says. What if the universe picks, I don't know, 12? 12 is not equal to 2. It's not the case that every natural number is equal to 2. This proposition does not hold. In fact, we can prove that it is false. Right? It does not hold. Right? Here's another more baldly wrong one, like my 2 equals 5. 3 equals 4. It's just not right. It ain't it. Take a breath. Okay. Prop is kind of just another type. If you want to name something, that's fine. Plus fact is a prop. It's equal to the proposition that 2 plus 2 equals 4. The type of plus fact is prop. If we print it out, it says, now this is, I think, very confusing what it's done here. Plus fact is equal to 2 plus 2 equals 4. There's two equal signs there. I'm not a fan. I wish they'd printed parentheses around that. But, okay, plus fact, the proposition, is equal to 2 plus 2 equals 4. The proposition. Because prop is an ordinary type, we can use it in other definitions. So here's a proposition that asserts that given a natural number, asserts that that one is 3. So is 3 is a function. You give me a natural number, I'll give you a proposition back. So for example, is 3 0? That's the proposition that 3 equals 0. Let's see. Excuse me. Is 3 5? That's the proposition that 5 is equal to 3. Both those do not hold. This is the proposition that 3 is equal to 3. That one does hold. A thing I want to stress again. Sure, prop is a new type. Fine. But the evaluation of this function is 3 that returns prop. It's the exact same substitution model that we've seen before. Right? Just plug it in. Okay. So functions that return propositions, we're going to call properties, right? Which is a little different from predicates. Functions that return booleans, we've called predicates. These we're going to call properties. The distinction is artificial and one just sort of for convention, but it's convenient to be able to really be able to tell the difference between propositions and booleans. We'll talk more about the real difference later on. For now, it's important just to keep in mind that a proposition is not a boolean. They're just different things. So here's a definition of a property that you may or may not have heard before. This says injective. F is injective. So an injective function says no two inputs share the same output, right? If I give you two different inputs, I'll hit two different outputs. If I give you two inputs and they hit the same output, those inputs need to be the same. So we say that here. So we have a function f from A to B. Maybe to clarify this, right? Type there. And then we say, okay, for every xy of type A, if f maps x and y to the same output, then x is going to be equal to y. Right? This is an important property of functions. We'll get to see a lot more about injectivity later on. Right? Now it happens that S, the successor function, the constructor of nat, is injective. It turns out every constructor is injective. We'll talk more about that later. The proposition that pred, the predecessor function, is injective. Right? That's this one. If we print it out, oh well, it's going to show us, unfortunately, here a little more detail than we want. So it's saying if I do, it's sort of run pred all the way. That's maybe not the most helpful thing. So injective pred, okay, that's a proposition. That proposition doesn't hold. In fact, I can give you what's called a counter example right here. 0 and 1 are two inputs that when given to the predecessor function give the same output. Okay, one last thing, and then we'll go through some quizzes that are meant to sort of test your understanding and like heighten your sort of like clarity on what propositions are. So the last thing is, here we've used this equality symbol to mean equals, but that's just another notation for something called eq. Right? Eq is a thing that you give me two things of the same type, and then I'm the proposition that they're equal. So check eq 3, 3. And then in fact, you'll notice Coq prints it out as 3 equals 3. Check eq 3, 5. Okay. Check eq 3 true is a type error. You are not even allowed to utter this statement. Excuse me. Right? You're not even allowed to utter this statement that 3 equals true. You can write 3 equals 3, that's fine. But if you write 3 equals true, Coq says, not only is this not a thing that holds, it's a thing that I'm not categorically willing to consider. Just like our lists and our trees were homogeneous, so is our equality. We'll only consider equalities between things of the same type. Okay, with that out of the way, I want to go through these remaining quizzes just to talk about like some nuances around what is and isn't a proposition, and hopefully this will heighten your understanding. Okay, let's start. As usual, I'll read the question, give it a pause, then we'll discuss the right answer. What is the type? of this expression. So this is a proposition. Here we have a term of type nat. Here we have a term of type nat. It's an equality. It'll be a prop. I didn't ask whether or not it was provable, but it is. This is 1. The predecessor of 1 is 0. What is the type of this expression? So again, this is a perfectly good proposition. We saw in our grammar up here, right, that a proposition is either for now an equality or a universal quantifier followed by another proposition. So for us, here we have for all n is a nat, and then now we have an equality in terms of n. The left-hand side is a nat, the right-hand side is a nat, looks well typed, that's a good equality. This is a proposition. This one is also true. Right? The predecessor of successor of n is just equal to n for any natural number. What's the type of this one? So this is, again, a perfectly good proposition. Right? We have a quantifier. Everything here is well scoped, right? We're referring back to this n that's of type natural. Successor of predecessor of n is equal to n. Well-typed homogeneous equality. Everything's looking good. Now, maybe you said not typable because you know that this one is false. Right? In particular, if n is equal to 0, this doesn't hold. You would be wrong in saying not typable, though. You'd be right if you said not provable, because it's not doesn't hold, but it is still a proposition, just one that we can't prove. What's the type of this expression? Okay, so this starts off good. It says, okay, for all n is a nat, and then this is well scoped. We only refer back to n and other definitions, but this isn't an equality. And right now, all of our propositions have to end in an equality. So this is not typable, right? This is a term of type nat, and the thing that comes after your for all here, that has to be a prop. It has to be a proposition. So the right answer here is not typable. Okay, we're almost done. What is the type of this expression? Okay, hopefully this one was easy. This is nat arrow nat. There's no propositions involved here at all. Little ringer. What about this one? Okay, well if that above was nat arrow nat, because nat is the type of this thing, then this is going to be nat arrow whatever the type of this is. But wait a minute. That is a proposition. So this is nat arrow prop. Which of the following is not a proposition? Let's do some process of elimination. This is an equality that's well typed, looks good. It's not provable, but that's fine. Another good looking equality. This is of type bool. Okay, so this one's not a proposition. This one is an equality of type bool. We have EQB, which is computing whether or not two natural numbers are equal, but is not the same as the equality proposition. And we're saying that's equal to false, correctly, right? Because EQB 3 plus 2, 4 is the same as EQB 5, 4, which should return false, so this will be right. And then for this one, okay, that wasn't very nice. What does that arrow mean? Okay, we'll see more about what that arrow means later on. For now, let me just say that this is indeed a proposition. Okay, that's it for now. I've got some more proofs coming. I'm hopeful that the next videos will be much shorter than this one. Had a lot to talk about here. What we're going to get started with is do some simple proofs, and then we'll learn about some more kinds of propositions and see where we get. All right, looking forward to it. Talk to y'all soon.